In Homer's Odyssey, the protagonist has to guide his ship through a treacherous gap. On one side, Charybdis, a terrifying whirlpool monster. On the other, Scylla, a six-headed woman who wants to claw out your eyes, then drown you to death. But although these monsters are fictional, Odysseus' passage has been identified with a real place, the Strait of Messina, between the island of Sicily and the toe of Italy's boot. The strait is famous for its treacherous conditions, strong currents, and yes, whirlpools. But the strait has another interesting quirk. The seas on either side of it have opposite high and low tides. Only a narrow strip of water separates high tide from low. It might seem impossible, but it's all down to a simple quirk of geography. The Mediterranean Sea, the body of water that separates southern Europe and North Africa, is divided into a whole bunch of smaller seas, defined by the way they interact with the coastline. Two of those seas, the Ionian and Tyrrhenian seas, both cradle the coast of Italy. The Ionian Sea is underneath the boot, while the Tyrrhenian is west of it. The Strait of Messina between Italy and Sicily connects them. Now, besides the aforementioned mythological significance, these seas have another peculiar property. They're in tidal opposition to each other, which means that when it's high tide in one sea, it's low tide in the other, which sounds a little weird. After all, the two seas are basically in the same spot. They're each other's next-door neighbors, which means that the forces driving the tides, the moon, the sun, and the rotation of the earth, should be acting on them in roughly the same ways. So it doesn't really make sense for them to have different tides. But to break down why this is happening, we first have to zoom way out to what causes tides in the first place. Imagine planet Earth without any land on it at all. Just a huge spinning ball covered in water. When the moon's gravity pulls on the planet, it's easy to imagine a section of that water actually bulging upwards, drawn toward the moon's pull. This is called the tidal bulge. Now, the Earth rotates while the moon remains relatively in place. So imagine that the Earth rotates under the bulge and it ends up moving across the entire planet. Right in the middle of that tidal bulge, sea level would be higher, and the area directly under the bulge would experience high tide. The size of the tidal bulge isn't consistent all the time, though. It's modulated by the sun, which also pulls on the water. That's why high tides are higher during times when the moon and the sun are pulling in the same direction, and lower when they're pulling against each other. The moon and the sun don't create water out of nowhere. The extra water that goes into the tidal bulge has to come from another part of the ocean. You'd think the water would come from the far side of the Earth, but it doesn't. There's a bulge there too, and that's because the Earth itself is constantly spinning. The Earth's inertia creates a counterweight, a second tidal bulge exactly opposite of the first tidal bulge. Between them, you have two areas of lower sea level, which we would consider low tide. So, on this water planet without any continents, any given location would experience 2 high tides and 2 low tides a day. But the thing is, we do have land, and land makes tides a little more complicated. Except for a few low-lying islands and the occasional sandbar, the tidal bulge can't pass over land. That means that the tidal bulge is constantly crashing into the coastline, and those coastlines can change the properties of the tide. This is why in some parts of the world, we can have particularly dramatic, spectacular high tides, because the coastline funnels that rush of water into narrow inlets that amplify the force of the tidal bulge. We'll explain why the Mediterranean is different in a sec, but first, this quick ad break.
Thank you to our Presidents of Science, Binor the Drunk Dwarf, Charlie Stanley, Harry Plumley, and Raz Tarash for supporting this SciShow video. You can be like our Presidents of Science and help Complexly keep spreading science knowledge and sparking curiosity in lots of ways, no matter what your budget is. The lowest barrier free way to help out is to, keep watching these videos. Bonus points if you comment and share, especially with teachers. We hear from a lot of teachers that they use our videos in the classroom. You can also check out our merch at complexly.store, or you can sign up for our newsletter and find out when we launch new and exciting things. Finally, you can join our Presidents of Science and other patrons who support us at patreon.com/SciShow. Thank you so much for your support.
The Mediterranean Sea is not one of those places with spectacular high tides. In the Mediterranean, there's sort of too much coastline. When you look at a map of the Mediterranean Sea, one of the first things you might notice is how enclosed it is. While the Mediterranean does have a few points where it meets larger bodies of water, those points are relatively narrow, which means that not a lot of water can leave the Mediterranean or come in at any given time. That means for tidal purposes, the Mediterranean is a bit like a bathtub. When the sun, moon, and earth start doing their thing and the tidal bulge moves over the Mediterranean, it can't just borrow water from the Atlantic to have sea-wide high tide. The water that rises with the high tide has to come from somewhere else in the Mediterranean. And since the moon is pulling on the entire Mediterranean at once, this kind of results in the water sloshing back and forth ineffectively, which is why tidal cycles in the Mediterranean are shallower than in other parts of the world. And I really mean shallow. Most of the Mediterranean is considered non-tidal for all practical purposes, with tides on average being about 30 centimeters high. But while the tide in the Strait of Messina isn't that high in the grand scheme of things, it's known for having really strong tidal currents. So strong that the area is actually being considered for tidal energy. Those currents are constantly moving, rushing in both directions through the Strait of Messina. The strait's geography contributes to those odd tides in the Ionian and Tyrrhenian seas. While it's high tide in the Tyrrhenian Sea, water flows in from the Ionian Sea through the narrow Strait of Messina, and vice versa. When the tide in the Tyrrhenian Sea goes down, it rushes all the way back to the Ionian Sea through the Strait of Messina. This happens on a semi-diurnal period, which in tidal speak just means that it happens about twice a day, creating a phenomenon that looks a lot like a normal tide. This seesaw means that the tides in both seas are always going to be opposite of each other. But that's not all. The seas might be in about the same part of the world, but they're separated from each other by enough land to be chemically different. The water in the Ionian Sea, for example, is saltier than the Tyrrhenian. Saltier water is denser than fresher water, and whenever waters of different densities mix, they can cause some really gnarly whirlpools and other instabilities. These smaller disturbances, combined with the really huge whirlpools in the strait that come from all that water rushing back and forth, are what make it a really deadly place for mariners, making the strait known for its wild, strong currents and deadly whirlpools. It's hardly surprising that the ancient Greeks may have imagined monsters to explain the place. Makes you wonder what other sea monsters might be lurking out there.